Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're gonna talk about global power grid. So let's dive right into it. Now be mindful, this idea of global power grid has been many names, many companies are trying to initiate it. Some corporation like for example, European Union is trying to unionize the whole goddamn system in their union, so to say. Basically France, Italy, whole of Europe want to have one grid. USA right now has 4 grids, they want to combine them into one grid. India wants to do something similar. So the core logic I want to explain. So before that, we have to understand what is electrical grid. Now I have made a dedicated video about this, so I'm just gonna be touching briefly on it. So what the hell we are talking about when you're talking about grid? Right now, current paradigm is you're gonna have large power station. Does not matter how big. Generally, it's big, huge, 1000 megawatt, 1200 megawatt, 12,000 megawatt, something bonkers. And you have this system somewhere in remote area, and then it's gonna pump the electricity using large transmission system, basically AC high voltage power lines, and it's going to distribute it among a very large amount of people, and then there are going to be a lot of consumers. So that's the current logic. You have large power plants, large distribution network, and then you give it to the customer. That's the current operation of modern electrical grid. Now there is a very big paradigm shift right now that's happening. Now what's happening here? People want to shift away from super huge power generation capacity of thousands and thousands of megawatt to few hundred megawatts. So basically fewer huge generation system and then lot of smaller generation units. That's the whole thing. For example, a single wind farm is not going to be very powerful. It's going to be barely, let's say, 100 megawatt to 600 megawatt. You can have like few large ones, you can have like, let's say 2000 or something like that, but you're not going to have like, okay, this place has bonkers amount of system. You're going to have them distributed. Is like, okay, here in this state, let's say they have 600 watt, in this state they have 200 watts, in this state they have 2000 watts. You get the point. So they will have a lot of small generation units. Now why these things are happening? Simply because renewable is becoming cost competitive. Nobody gives a damn about planet, and you have to understand it. You have to accept it. If you want people to go to renewables, you have to make renewable effective, basically good for their wallet. Thankfully solar is reaching a point where it's good for their wallet, and wind is also. It's far behind, but at least people who are investing in it right now, they can be like, I can see some potential there. So solar has already reached a point, and specifically in some expensive countries, it has reached a point where it's like, dude, it's actually cheaper if you just do solar flat out compared to coal systems, is flat out cheaper. So people are doing this. However, renewable comes with a serious consequence of being intermittent. Basically you cannot rely on it. Even a solar farm, even during the day, you cannot rely on it. Basically it's not like, oh, I made a, let's say 1500 megawatt solar farm is gonna give me 1500 megawatt. That's not gonna happen. You're gonna have fluctuation. You can literally have like a very GG amount of power in July, and you can have very low amount of power in June. So June, not even June, like January, you get the point. So fundamentally there is a lot of fluctuation, so you cannot rely on it. Right now our power system is like, we are getting 1600 megawatts of power plant, we are getting 1600 megawatts of power plant. That you don't think about it. But with renewables, it's not like that. And wind, they also have a lot of fluctuation. So there is a lot of intermission there. That itself would be manageable because, like, balancing one unknown. But problem is demand is also not constant. Right now you are not in a position where demand is like, okay, this state is only consuming 2000 megawatt. Then it's like, we got this, we can manage it. But what we have is like 2000 megawatt is the average. So reality would be some peak times it could consume as high as 6000, and low times it could go as low as like 200 megawatts. Like literally that kind of variation happens in certain places. So that's the shift that's happening. Game is changing. Fundamentally game is changing. So one of the core aspects that you have to understand about renewables is they are very location dependent. They are almost like hydropower plant in that regard. So what does that mean? That simply means if you have a fixed amount of money, let's say government central reserve system has a certain amount of money, like take this GG amount of money, make me a solar farm. Let's say you take an example of India, you can make that in some place in Rajasthan and you're gonna get YOLO amounts of power, or you can make some place in basically South India, which is land is cheaper, yeah, capital cost is lower, but you're not gonna get a lot of power, or you can place somewhere where it rains most of the time, so it's not gonna be useful. So that's is the core critical aspect that you have to think about. It's like, okay, where the heck you're gonna place this thing? And that fundamentally creates a system where you have supply and demand, they are far apart. Right now our current logic is you're gonna have a large city and you're gonna have a large power plant nearby as in like, you can literally follow the power lines and see there. So at this point in time it will be like, at the one corner of India we have this, and another corner we have hydropower plants, and another corner we have geothermal system. So you get the point. Right now we're gonna want to distribute everything. So what's the problem with that? Fundamentally, AC electricity does not like to travel that far. Fundamentally, you cannot do that. There are many reasons. First of it is like the cable. You have if you pay attention to basically high voltage power line, they are never one large cable, they are like multiple strands cable. The simple reason is AC electricity does not travel in fat wires. It flat out does not, it ignores the center core. Only like if this is a fat wire, electricity is only traveling around the skin, which we call skin effect. Awesome name. It does not go through the core. DC does not have that issue, but AC does have that. And there is another really painful thing which we call capacitance. Basically the whole conductor, because it's fluctuating magnetic field of AC electricity, is behaving like a capacitor, so to say, and it's losing energy. What does that mean? That simply means you can take hundreds of megawatts of power and you can send it, let's say 1000 kilometer. It will not reach at the other end. No matter what you do, no matter what voltage you send, it will simply not reach the other end, no matter what you do. That was the same issue China was dealing with when they wanted to build large hydropower plant in some location and they want to transmit electricity very far away. It's like to AC simply will not go. Same issue was faced by a lot of European countries when they wanted to build offshore sea based basically wind farms. Electricity will not travel this far, especially AC electricity underwater. Yeah, forget about it. You can send thousands of megawatt, barely get some percentage out of it. So that's a lot of wastage. And you can easily notice this in Indian railway. Basically, you're traveling in the railway, it's like AC line. Like how the heck that's going for hundreds of kilometers? Notice that every few kilometers there will be a substation that's pumping the electricity. So that's the reality. So how can we manage it? Like we want to put like, okay, something here, something here, something here, something here. That's like countries apart. How the heck you gonna manage that? Thankfully, we have latest technology known as high voltage direct current. High voltage, because otherwise like ampere would be too huge. So we want to do high voltage system, and direct current simply because it will reduce the what we call skin effect. So you can actually use fat cables. And another aspect would be it can actually transmit. Like you can send 1 megawatt, it will go 1 megawatt at the other end. Like again, there will be some loss because you are not using superconductor, but it will be negligible compared to AC loss scenario. So fundamentally people are doing that. And not to mention these are actually cheaper in terms of transmission wise, because you only need 2 conductors, or heck, if you really want to, you can make them with 1 conductor also, rather than 3, which is needed for high voltage AC system, because they are generally done in 3-phase electrical system. And the inverter system that is needed to pump this kind of GG amount of electricity was ludicrously expensive. Like imagine going to some manufacturers like, yeah, we want an inverter. People like, okay, we got you fam, how much you need? 800 megawatt. Is like, what? Right now that's like a common jump change. Like you can literally go to ABB website and it's like, yeah, I want 800 megawatt inverter. They're like, yeah, just take it and go. So distance has been taken care of. We got the technology, we can solve this. So fundamentally you can have solar farms in Rajasthan, wind farm in South India, basically in a lot of hydropower in northern India, and you can mix all these power like hundreds and thousands of kilometers apart, and you can get one global grid. So let's take a look at a very critical aspect of electricity, that is stability. Basically, electrical grid is something that you don't think about. It's like I plug my stuff in, it works. You don't think about it. That's the whole point. It has to work 100% of the time. There is no off day, there is no Sunday, there is no Christmas. It has to work. So fundamentally, there are 2 core factors that electricity must control. That is frequency, as in like 50 hertz or 60 hertz. In case of India, it's 50 hertz. In case of USA, 60 hertz. That must remain exactly like that. Like again, there is a little bit of variation, but the variation must be less than 0.1%. And then you have voltage. Now voltage does have a bit more leeway, so you can easily notice a power plug or something like that, and you will see that it says like 200 volts, and you will see your appliance, they will say from let's say 200 volts to 250 volts. That would be range. And like in India, because of poor power conditioning, we have a scenario where like all our appliances are designed in such a way they can run from 180 volts to basically 220 volts. So you get the point. Like you have a bit of leeway with voltage, but for stability and health of everything that is connected to the grid, you want to keep these 2 things stable. Thankfully, that is achieved in our current grid because of spinning mass. We have giant steam turbines, which are big, which are heavy, which are hundreds of tons. What does that mean? That simply means no matter what you do, you cannot slow them down. So once they get to full spinning and they are rotating, let's say 1600 RPM, they're like going at 1600 RPM, computer is monitoring the RPM, and you directly started an induction heater that is like melting iron in a foundry. Huge power load. It's gonna dip it down. Energy cannot be created, not destroyed. So generator will go into the load, and that spinning mass will lose energy. However, because of the huge mass we are talking about, and given the fact there are hundreds of generators connected in that way, that mass is almost unstoppable, at least for a small instant of time. So you can literally go, okay, my frequency went from 50 hertz to 49.001 or something like that, 49.999, something like that. Like little bit of frequency dip. Computer is like, okay, RPM is dropping, open the valve, steam will come in, RPM will go up, it's like still stabilize, and during this time boiler will be like, okay, we have more demand, go YOLO on it. So That's how our current grid is stabilized. So many spinning masses, fundamentally you cannot do anything to that will stop it. So that's awesome. But how the heck you gonna do that when you have solar panels here? That can be achieved by HVDC, because that's a system that is taking DC. DC is coming from inductors, it's coming from capacitors, so it has a very there is a lot of stability there. So how the heck you gonna fine tune it? The inverter, that's what it does. It basically controls the frequency and voltage, so you can get a lot of control. Specifically if you have large grid and you are mixing power from different sources, HVDC is great for that. And then another aspect that you have to deal with, that is called grid scale energy storage. This is something that we do not deal with right now. However, it is also becoming more cost effective. Right now in USA and European Union, electricity is ludicrously expensive. Reason for that is simply because once the power goes beyond the certain capability, basically beyond the base load, they start what we call peaker power plants. It's like these power plants are only made for high spike loads. They only run for a few hours a day most of the time. Consequence of that, they are very expensive. Like per kilowatt hour you take from a nuclear power plant is, let's say, $5. Again, I'm just giving you a rough example. It would, from a peaker power plant, it would be 20. So to balance that, like, so customer does not go like, what the heck, the base price is increased in such a way, so it makes your per unit cost much higher. So right now people are doing, specifically Elon Musk is trying to do, is have giant battery banks. It's gonna take power when there is low demand, and power plants do not want to tone down, because they are making money by selling electricity. If they are not selling electricity and they are toning it down, curtailing their performance, it's not a good thing for them. So it creates a scenario where you have a lot of wasted electricity that would have been stopped. So instead of stopping them, put them into a battery bank and sell it during peak hour. Awesome. So that way the price can be managed much more effectively, and many people have already started doing that. Like in USA, Australia, European Union, and small villages, they are very good for this kind of scenario. And in small villages, you can literally isolate the whole system just on solar alone. So grid scale storage is a very necessary kind of thing. However, one thing you have to understand, you cannot go all solar. Fundamentally, you cannot do, you will destroy yourself, simply because solar only works in daytime. You need wind, you need geothermal, you need hydropower, you need biomass system, just so you can have something at night. Because if you don't, you have to have 3 times the production capability during the daytime, so you can store the 2 times extra that you are storing in the power bank, and you have to do it daily. That is insanely large battery banks that you are talking about. And grid scale storage, we're talking about megawatt hour, basically 100 megawatt hour. That's not a lot. Like, you're a big city, peaker power plants, they go bonkers. They go like 600, 700, or 1500 sometimes. So you can understand that. And not to mention, it cannot sustain it. It's like, yeah, it's a battery, it will do good stuff, but it's not gonna last very long. So that's an issue. And if you are talking about pumped hydro, that goes to like 2000 megawatt hour. That's a lot of capacity, but still 2000, and we are dealing with 20,000 demand. So you have to mix your power sources. That's critical aspect. It must be mixed. So you have solar, you have wind, you have wave power. Again, it does not matter. It does not need to be like backbone power supply. It has to be good enough where it's adding something, so your battery demand goes down. Otherwise you will spend most of the money in the battery itself. So that's how we can achieve stability in such a grid like that. And that's why people want to connect whole nations through this, is simply because if European Union works that way, you can literally have a scenario where no matter what happens, some country, some place in whole of European, because of the geographical size of it, it's like, dude, sun is still rising in there, sun is still setting here, like, dude, we have more than enough power, wind is still blowing here, this is still happening here. Like, they will always have a scenario where if they overproduce it, somebody is there on the grid at any moment in time. It's like, dude, I can buy that, don't worry about it, I can buy that. So they are using brute force, but most of the time you will not have that luxury. Like in India, you cannot have that luxury. So mixed sources is kind of necessary. Now smarts, this is our final solution at this point in time. Wastage must be reduced. That's why we want to shift from AC to HVDC, because we are wasting significant amount of electricity just because we are using AC system. Now, it was awesome in 1990s, 1900s and all that jazz, but right now we have better system. We have to move into it, because every megawatt wasted, it's a megawatt wasted. So reduce must be wasted, basically reduce the waste. Then you have to talk about smart grid becomes compulsory at this point in time, because you do not have a very GG amount of power supply. It's like, dude, this is a power supply, it's a constant, it's gonna give this much. We don't have that. You want to have smart grid. What will that allow you to do? That will simply say, hey, if power companies is like, dude, we are not getting a proper solar output, they can send a signal to your smart grid, to basically home appliances, and they will be like, let's start one by one. So spike is the bad part. You don't want spike. So you, instead of like, let's say for some example, if you average it out, everybody starts their basically water heater at, let's say, 6 p.m. So smart meter would be like, okay, 50% will start at 6 p.m. and 50% will start at 6:30 p.m. or even 10 minutes. If you delay that spike, everything awesome, grid is healthy, no blackout. So that will becomes a kind of necessary with smart grid. And then you have a small scale options, because yes, we can do large scale grid storage. It's not that practical. However, small home scale storage is doable, and most people stay in their home most of the time. So if you have basically they are sleeping and all that jazz, and because of the fact the world ended in 2020, home is the primary power consumption. If you have battery bank exactly at home, you don't even have to do anything. You'll just run the system on basically home grid when electricity is cheap, and when it's expensive, okay, run on battery. That's how people are selling Tesla battery banks. And there are other systems like power vault and all that. Yes, you can do that right now. And heck, you can even have your own solar farm in your rooftop and directly pump the power here and get a stable, clean output to yourself. It can be done right now, and many people are doing it. It's just expensive kind of thing. It's like buying 2 or 3 electric vehicles, but doable. It's doable. If you have deep pockets, you can do it within reasonable amount of time right now. So smarts will allow us to have a lot of mixed things to save ourselves, because many times I see people are like, oh, why don't we do solar, why don't we do wind? Or it's like we cannot achieve what we want to achieve just on that, like do this, done. That only can be done if we achieve fusion, which I have very low hopes on. So right now, removing nuclear options, you only have the reality of that you have to mix things. You have to mix as many things as possible. Heck, wave power does not give too much power, does not matter, just add it, just keep adding as many things as possible. So you do not have to worry about basically nighttime system, and battery bank always can be charged, so it can handle the peak powers. So smarts is our current solution, and it could not have been done. Like if you were talked about, people is like, oh, in 1990 we're gonna have a system that's gonna communicate at hundreds of megabyte per second to hundreds of systems. Like what the heck are you smoking? Right now it's like we call it 4G mobile phone, old technology. So this was my presentation on global power grid. I hope you liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike. Press it twice to show me extra disappointment. Please leave a comment because I try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.